Seriously, I'm gonna say that my office hours are gonna be Tuesdays and Thursdays. Maybe you've seen that on the schedule. So, Virgil's office hours. It's Tuesday, 6 p.m. Where the workout group is. I don't know, I think it's Ryder, some room at 6 p.m. With the tutors and PAs. This is for regular stuff. So on Tuesday, I'll primarily help with the basic homework. It won't be just you, it will be all the 670 students or so. And Thursday will be at 6 p.m. Also where the group is. I think Ryder will check the room. That's the honor stuff. So if we have to talk about advanced stuff, that will primarily happen on Thursday, because Tuesday the homework will be due, so we need to deal with that. I'm assuming you guys won't have that many questions about the homework, and maybe by Tuesday it's pretty much all set. So I'm happy to go there Tuesday at 6 p.m., see who needs me, and maybe by 7 or so, if you guys show up, we can talk about more advanced stuff. So before we start, stuff going on here. Before we start, I would like to keep working with hints for that square game problem. Anybody solved that yet? No? Like I said, that's an honor thing, so you should not expect a mechanical, here's a formula, apply the formula, get an answer. That's usually what happens to the most homework problems at regular CS 1800. Honors problems will definitely involve thinking. They're not that hard. They're not like International Math Olympiad hard, but they require thinking and hints. And that's why we have Thursdays office hours to talk about those problems. I also think some of these problems, particularly the first one, will help you a lot to work in groups. Everybody, group of 3 or 4 or 5 people come up with ideas, try it out different boards to see what happens. So here's my hint for today on that problem. We already talked about mirror boards. Remember that from last time? If there's a mirror board, the strategy is pretty easy. As player B, I'm just going to repeat the move of player A on the mirror row, and that's guaranteed that I'm going to win as player B. But how about the mirror board that's like this? Non-mirror board, sorry. Who has a winning strategy? Yes.
The second player has winning.
Also player B, just like in the mirror boards, right? I think you can figure that out, that pretty much no matter what you do as player A here, player B has a winning strategy. So my point is, this is not a mirror board. I want to recap a little bit what we said we want for mirror boards as a principle, because the principle applies here too. What we're looking for, an invariant property that has, I already said this last time, I didn't call it invariant, but that's how it's called. We want the invariant to be true after B moves. And so that has to be possible. B should always bring back that invariant back to true, no matter what happens. And the invariant must be false after A moves. So B has to be able to bring it back. A has to be forced to do this. So it's like, I'm player B, I'm looking for a winning strategy. I'm looking for this invariant property that will force A to move away from the invariant no matter what, and allows me, player B, to do one move, meaning on one row, right? Because I can only move on one row. And also, invariant false must imply A cannot win. For example, a way to guarantee that A is not win is to say if the invariant is false, there's at least 2 rows, right? I'm not saying that's necessarily what we need, but if I can promise invariant equal true. So if the invariant is true after I move as player B, if I can guarantee there's at least 2 rows left, that's for certain that A cannot just finish the game in one move, right? Because he can only take rows from tiles from one row. He can't take 2 rows. So I'm not going to tell you what that invariant property is. That's the key to this problem. What is it? But I'm going to give you some hints today for how to look for it. That invariant property happened here because B has a winning strategy, even though this is not a mirror board. Right? First, I'm going to say, in this game, the tiles are really just for illustration. What really matters is their count, right? There is no order or something special with tiles. The board is really 1, 2, 3, right? And an operation of picking a row and taking some tiles means what? Subtract some number not below 0, because you can't take more than 2. If you pick this one, you take 2, right? So my first hint is this one. You can convert these to just counts. You don't need the tiles on the board. It's just a bunch of counts. And my other hint is maybe B move, that's part of the strategy. B can only take 1 row. Can only modify 1 row, right? Like A. Which row should that be? So as a general statement, I want to fix this board. It's one of the boards that B has the winning strategy. I'm only thinking myself as player B. How should I leave the board so no matter what A does, I bring it back to this property? And before we give more advanced hints, what should be the row that I take on?
Depending on how player A moves, you want to take a row that would make the remaining game a mirror game.
If I can bring a mirror, that's fine, but maybe I don't bring it to mirror. The invariant property is more general than just mirror. It certainly is satisfied on mirrors, this property I'm talking about. But it works on more boards, like for example this one. Right? So, do we all agree that B has a winning strategy here? Is that obvious? Hands up who's with me on this. And if we need to play a little bit on paper, you can do that after class, try it out to see that B wins here. So now since I know B wins, suppose I have this board. I'm player B and I didn't move. I'm here, B moves. Now, can I win this game if I move here? So B wins if A plays. Right? That's saying if I'm the second player, if I leave the board like this, I'm going to win. Well, what should I do here? I can't bring this to a mirror board. There's no move that will make this a mirror board, is it? But what can I do?
You can turn it into a row.
I can turn to that. On what row do I need to move to do that? Right, so my move should be take this out.
But you should have one more.
One more. You're right. Right? Which row did I move on? Just gross is speaking? The biggest one. Okay, how about a different example? Again, B moves. That's me. I'm only thinking myself as player B. Which is like, what should I do so that when A moves, the other player next, I can bring it back to this nice invariant property, which you have to find. That's the key to this problem. Suppose the board looks like this. Can I somehow do something here to bring it to a well-known winning position? What? Somebody else. Yes?
Take 3 from the middle.
Take 3 from the middle. again, the longest row. So there is some magic trick in this invariant property that you again need to find. And I can already tell you it has to do with counts only. Obviously it has to do with counts because there's no other description. The description whether tiles or counts is equivalent problem. There's no order or anything like that in the styles per row. You gotta do something with the longest row, aka something means what? Subtract a bunch of tiles, which means reducing this longest number to something. So you can only move on one row. You can only reduce the biggest value. That was 5. I reduced it to 2, right? And in here was how much?
7.
Reduce it to 3, right? That was my move. This one move on one row, which is the longest row, has to somehow check out the invariant property on all the other rows, right? So that invariant property has to do with all the rows, obviously, because if you take one row, you modify it, it's a different board. But I can only move on one row, so somehow think about, I have one row, the longest row. I have to delete something, a number. When I delete a number, I can get from 5 to anything smaller than 5, right? 4, 3, 2, 1, 0. Or from 7, I can get to 6, 5, 4, 3, 2, 1, 0. And that has to somehow, that number I get to below 7 has to check out to be the magic value that invariant property gets satisfied. Remember invariant property? I have to bring it to true in one move. A will be forced to move it to false. And then it's not possible to win if I leave it at true. I'm not interested to hear what's the invariant property right now. But you guys can totally discuss this on Piazza. I mean, this is not considered cheating at all if you go on Piazza and say, I believe the invariant property is blank. What do you guys think? You still have to write your own solution strategy with a proof. But discussing it, here's what I think is a strategy, whether it works or not, is totally fine.
Can you go through that second bullet point?
What?
The second bullet point for under looking for invariant property?
This?
The second bullet point.
This?
Yeah.
Can
you go through it again?
If invariant is false,
Yeah.
after A moves. So this saying that if I leave the board with the invariant equal true, A is going to be forced to put it on false. In other words, invariant property will be true on this board. But when A moves, it's not going to be true. This invariant property, if you execute just one move, it switches to false. So that allows me to bring it back to true. Just a hidden hint here was that all the other rows, when you think of this invariant property, you really want to think of the longest when B moves. So that is in here. B moves is the longest row versus the rest of rows. So somehow that invariant property has to be able to say, you look at the rest of the rows except the longest one, and you adjust the longest row so that the combination of these rows together and with your move on the longest row, check out the property. Right? So you got to think of all the other rows as together somehow. You can't analyze each row separately. There's something that says, here's all the rows together, and here's the longest row that you can adjust. So how do you adjust it to kind of check out magic? There was a question here.
So let's say I don't know how to write the proof. And you've already explained you can consider the squares in terms of heights. How am I going to figure out, I'm going to write a proof like this between now and then?
So that's fair. I don't expect any formal proof, and I'm not worried for this problem about how do you formally write the proof. Because we're at the beginning of the term. By the end of the term, we're going to get much better at writing proofs. I'm much more interested in finding that property and argue it informally, in words, in English, why it works. And so I'm not expecting mathematical, theorems, proofs, but I do expect, here's why it works, this property. Here's why I can adjust the longest row so that together with the other rows, which I'm not touching, obviously if I touch the longest row, I can't touch the other rows. Why is it that all together checks out, has a property that's how these three bullets problems?
And are you expecting that written up in tech, or is that?
I think that has to be, if it's in grade scope, it's gotta be written up. Yeah, but text, no big difference writing it by hand or LaTeX is more difficult a little bit with all the math equations. But if you type text, I don't expect a long answer anyway. So like half a page probably too. All right, so that's my hint for today on this problem. Let's do binary representation, right? So what did we do last time? Let's take this number here, 105. That's in base 10. If I don't say the base, it's base 10. And how did we say we decompose this in base 2? What was our strategy?
Go for the largest power of
What's
two.
the largest power?
64.
64 plus
32.
plus.
16.
Can I fit 16 in there?
No.
16 plus 64 gives me 80 plus 32. That's too much. I cannot fit 16. What else can I fit? Can I fit 8?
No.
8 plus 32? 40 plus 64?
Yes.
Can I fit 8?
Yeah.
And then? 1. So now the right way to do this is 2 to the 6 plus 2 to the plus 2 to the.
Third.
So remember my old strategy for writing those bits. 2 to the 6 is 1 followed by? How many digits? 6. 1, 2, 3, 4, 5, 6. I put those dashes to not get confused later on. I do that actually with another student. You see those lines and everybody asks, what's up with those lines in your papers? Well, I want to count the digits properly. You don't have to put the dashes, but that helped me make sure I have the right digits. So where's 2 to the 5th going? If this is 2 to the 6, 2 to the 5th goes right here, right? And then 2 to the 4th, 2 to the 3, to the 2 and 1, to the 0 is here. Okay, everybody got that from last time? There is another method that I can use to achieve this. I'm just saying it as an alternative. Unless the method is specified in the homework, you can use any method you want. So sometimes it's specified. And the other method is integer division, which you probably have seen, that says if A and B are integers, and B is, say, positive, right? I can divide A with B, and I get B times a quotient plus a remainder, right? So we call this quotient, and R is a. These are all integers, right? Quotient and the remainder. And the remainder is in what set? When I divide with B, what possible reminders can I get? 0, 1, 2, up to the last reminder is B minus 1. You can see how this is very similar to the whole basis. What are the digits in base B? Remember from last time? 0, 1, 2, 3, and B minus 1. So that's kind of the connection there. Reminders and the digits are the same set. And there's a theorem that you get to prove by tomorrow that says Q and R are unique. Just kidding. No, we should be able to prove this theorem. This term, we took the number theory out of the term because you get to start in a different course, and we restructured this a little bit. Obviously, it's a lot easier with number theory to prove this thing. But it's totally within your scope and ability to prove this theorem that if you have A and B and you require a quotient and remainder with this property, it's essential that you require R in this set and not just some random R. Then Q and R must be unique values. In other words, if I divide 100 by 17 and he divides 100 by 17, we're going to get the same quotient and the same remainder because those are unique values. unless one of us does the division wrong, right? It happens to me all the time. So how can I do this? What should I do to get, instead of taking the biggest power out, which is a kind of my preferred method to do so, what else can I do?
Well, you can say if it's odd, you subtract 1 and divide by 2, or you can say if it's even, divide by 2, and you know whether the number is
But
odd.
division will do that for me. I don't have to distinguish odd versus even. I'll just do the division, and I'll get an R, which is either, if I divide by 2, R will be what?
1 or 0.
1 or 0. So let's do that. So if we take 105, that's my number right here, and I divide by 2, so A is 105, B is 2, right? What am I going to get? 2 times, what's the quotient there? Louder? 52 plus 1. So that's my first reminder here, right? Where is this 1, do you think? Which bit is this one?
The rightmost bit.
Very good. So this is the right most bit, or sometimes it's called least significant. Why do you think it's called least significant? Informal common English.
Least value.
What?
Least value.
Right, out of all these bits, the one that has the least impact on the magnitude of the number is this one here, right? This is changing the number by 1 unit, while this one changes it by 2 to the 6. If I flip this bit to 0, I make a big impact. So least significant, make the smallest difference. It's on the right side. And most significant will be this one, right? Okay, so I got that bit, now what? Yes?
52 comes A.
52 is A now, and I divide 52 with 2, I get 2 times 26 plus.
0.
Like we said, these are unique. The nice thing about unique properties in all mathematics is that if you find them somehow, guessing them, for example, right? You don't have to worry because there are only one set of possible unique things. Once you find it, once you guess it, nobody can ask you why. That's the one you're looking for, right? So who's this 0? Is that 0 right here, right? In fact, who is 52? So 105 is the whole thing, right? That's 105. You guys believe me, right? Where is 52 in here? Yes.
It's all of the bits except the rightmost bit.
If I'm to read from here to here without this 1, actually not pretending it's a 0, just cutting it out, would I get 52? There's something going on here, right? Right? So see how you have to think of this, the right way to look at this is the exact analogy, that versus that, step by step. What happens here if I take a bit out like that, effectively? I eliminated that reminder, first of all, because this is 1 or 0, it's irrelevant. When I cut something out, it doesn't matter whether that was a 1 or 0, right? So I first make this a 0, so to speak. And then what operation mathematically corresponds to cutting the bit out? Divide by 2. So effectively, I remove the remainder first, because I made it 0. And then I remove this, and then I had 2 times 52. So by cutting a bit out, what did I do? I divided by 2, right? Is that always true? If I am to put a random number right here, really random, 1, 0, 1, 0, 1, 1, 1, 0. I don't know what number that is. If I am to divide by 2, am I going to get 1, 0, 1, 0, 1, 1, 1, 1, except the last bit? Is that always true? Cutting the last bit out, it's effectively a division by 2. Is that true in any base? Say in base 10. How do I divide by 10 in base 10? I just cut the last digit, right? If it's a 0, I mean, I have to nullify that reminder first to be an exact division. Whatever that digit is, make it 0 first, and then divide by 10. That gives me exactly, right? Let's be more clear what I mean. If I take 8792, that was our example, I make it first 8790, make the last digit 0 on base 10. And then if I have to divide by 10, what do I get? 879, which is exactly the part before the last digit. So that clearly happens in base 2 also. Getting rid of the last bit means division by 2, and you can see why. Okay, so let's keep going with the thing. What's my next step here? I want to get all the bits. So this is, I got this bit. How about next? 26 is 2 times 13 plus 0. This 0, it's going to be this 0. Right? 13 is 2 times 6 plus 1. This one here is going to be this one. And then 6 is 2 times 3 plus. And then 3 is 2 times plus 1. So I get this 1 that's in here. And finally, 1 is 2 times 0 plus 1. When I see this 0, that's a stop. So this 1, the last remainder, or this one, is the first one. So I can obtain this by repeated integer division, right? And I can do this in every base, of course. Because if I divide in base 17, the reminders will be 0 to 16. If I divide in base 25, I'm going to get 0 to 24, exactly what's going on. Now we can argue this procedure a little bit more abstract by looking at the representation. So how do we prove this? That this method and this method are equivalent. They give you the same answer. So we have a theorem here. This method is called most significant bit. Most significant, which is get highest power b to the k available, and then repeat, right? That was our method. Take the biggest power you can. That may fit multiple times, right? It might be that that just doesn't fit one. In base 2, it either fits or doesn't fit because the coefficients, the digits are 0, 1. But in base 3, what are the possibilities if b is 3? It can fit not at all, that's a 0. It can fit once, so that's a 1. Or it can fit, so available up to b minus 1 times. Right? In base 3, I may have to put that power twice. In base 7, I may have to put the power of 7, 0, 1, 2, 3, 4, up to 6 times. And least significant bit is that one. That means repeat integer division. So I have two methods, and the theorem says these methods are equivalent. We give same answer. So that's a proof that you guys have to do, but I want to give you a hint for how that proof would work. The easiest way I can think of to make some progress here is to look at my number in base B. Our number looks in base B, well, it has a digit, what did we say, digit 0, right? Times b to the 0, plus a digit 1 times b to the 1, plus a digit 2 times b to the 2, plus a digit k up to b to the k, right? And all these digits, di, belong to the set 0, 1, 2, up to b minus 1, right? So they have to be correct digits in base B. So how can I justify, for example, from there to there? I want to do the kind of looking at the base, simulate the integer division, and kind of show that I'm getting up the right powers. What's going to happen when I do the first integer division with B? What am I going to get? So the first integer division, who's going to be the remainder? D0, because everybody else is a multiple of B, right? When I divide by B, this is going to give me 0, reminder, 0, 0, 0. All those things are multiples of B, except this one, which is not, right? Because B at 0 doesn't count as a multiple of B. So reminder will be D0, and the quotient will be what? If I divide by B after getting rid of the remainder. Yes?
D1 plus D2 times B plus, like,
B at 1, right?
yeah.
Plus what's the last one?
DK times DK minus 1.
How many people see that? If I do the integer division, quotient and remainder with B, I'm going to get this remainder and this quotient. Hands up so I can see them. You don't have to raise your hand if you don't follow me. When I ask this question, it's because I want to know who's following me. This is a very simple check. If you multiply this with B and you add the remainder, you get that thing. I mean, check will be exactly multiply Q times B plus R to see if you get the value N that we started with. So then after the second division, who's the remainder? Same thing, right? This remainder is going to be D1, and the quotient is going to be D2 times B at 0 plus D3, B at 1 plus DK, BK minus 2, and you can take it from here and figure out where this is. It's pretty straightforward to finish the thing. To show that if I take the digits this way, I'm ending up with the same digits like taking the highest power. All right. So that's good. Now this integer division, it's kind of the start point for something called modulo arithmetic, which we won't do in this course. Just a little bit. Okay? We'll do a little bit. Modulo arithmetic is mostly writing this stuff with different symbols. The mechanisms of what happened is exactly integer division and additions with remainders and quotients. But we have a different notation. So anybody knows how can I write integer division with modulo arithmetic? Yes.
So I'm just going to take the first example with 105.
Oh, I would like to say that equation first and then
Oh,
the
okay.
105. So instead of writing A equal BQ plus R, how can I write it?
A is congruent to, or in parentheses, mod B.
I don't know if you guys seen this notation. Hands up who's seen it. It's just a notation. It says if you divide A by B with integer division, I don't care about the quotient here. Quotient could be some integer Q, but the remainder you get is R. Right? So it's not, I don't want you to think it's some fancy thing. And by the way, this 3-line thing, when I was a student, everybody got confused. Wait a minute, why is it 3 lines and not just 2 lines? Is there a difference between 3 lines and 2 lines? There's no difference. Like mathematicians just want to make it complicated and confusing. So a lot of things can be simplified to a more like easy stuff. You guys don't have chairs. Is that true? Yeah, why don't you get a chair from here? Sorry, let's see that. Seriously, and you can take the other one. You good like that? I'm taking your chairs to the camera. Sorry about that. So this is just a notation that says A integer division by B gives remainder I. How do we do that with 105? If we're going to say this for 105, what is that here, right? We're going to say 105 is what? 1 modulo. Right? So while we're not going to teach number theory, aka modular arithmetic right now, I do want to show you something that will help you understanding how bases work. That's typically part of the modular arithmetic stuff. So I'm going to draw a circle here. And when you do a numeration base, say base 2, it's useful to specify how many bits you're using. If you don't say, it means use as many as necessary. So in some problem you won't say, you say transform this number 105 in base 2. I didn't tell you how many bits to use, so you're going to use as many as you need. How many bits are in there? 7 bits are being used, right? Because I need 7 bits because of that 1, right? I can't represent 105 without the 7th bit, the most significant bit, because if I take one out, I don't have enough bits to represent. But let me say here I have 3 bits. So I'm going to call this 0 on 3 bits. 0 is 0, 0, 0, right? And this is something like this. 1, 2, 3, 4, 5, 6, 7, 8. This is going to be 1, 2, 3, 4, 5, 6, and 7. So of course we know what this representation is on 3 bits. This will be who?
0, 0, 1.
1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1. We all seen this. The maximum, that's what we did last time, you can get is 1, 1, 1, 1. How many ones you have there? I have 3. I could have done this with 4 bits. If I do it with 4 bits, how many ticks are going to be on this circle?
15.
Total, including 0.
6.
All right, so let's try that. I'm sorry to subject you to my drawing skills here. Let's see. If I am to do 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's see. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Which one's the last one I need? 15. All right. So this will be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1.
Wait,
Hold
now.
on. Hold on.
Second 0, 0, 1.
Sorry, too fast. 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0. 0, 0, 1, 1, 0, 1, 0, 0, 1, 1.
1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1.
Worked. I actually not just want to show you the circle. I want you to kind of picture in base 2 only, not in base 3 or 4 or 7 or 16, in base 2. What's the pattern with these 0, 0s and 1, 1s in there? So if I have 4 bits versus 3 bits, there's a kind of the same mechanism, right? It's kind of like this digit always changes from 0 to 1, the last one, but then this other digit changes in a different pattern, the second digit, and the third digit changes in a different pattern, and so on and so forth. I think it's useful to take a look at these 3 bits, 4 bits. You can draw one with 5 bits. How many ticks are going to be there? 32, right? And kind of figure out how the bits work in base 2. So this is extremely useful for modular arithmetic because in numeration basis and in modular arithmetic, this circle has a very corresponding analogy in how numbers work. What happens here, if I don't have enough possibilities to represent my number, like if I go more than 7, I don't have enough bits, right? So when I'm going to try to add 1, what happens in this direction? It's adding 1, right? So if I go from 7 to add 1, the value itself becomes 8, right? What's the relationship between 8 and this? And base 2, I mean. I can't represent 8 because I don't have enough bits. But if I kind of force myself to do it, how 8 going to look like? 1. 8 is this value, right, in base 2. Of course, I can't represent that value. You can see there's no space on the circle. But what's the relationship between 8 and 0?
I showed the same last time.
They have the same exact 3 bits. Right. So how about if I keep doing this? If I add 1 from 8, what am I going to get? 9. Who's 9?
1, 0, 0, 1.
Is that the same relationship? The last 3 bits add those 3 bits, right? And how about here? If I keep going plus, 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 instead of 3, I'm going to get what? This is 9, right? This is 8. Again, I can't represent them on 3 bits because I don't have enough bits. But if I can go, kind of go on this circle to see where would they be, what would be here? 11 would be what? 1, 0, 1, 1. That's 11, right? And no surprise, the last 3 digits are the same. Why? Because the difference between those two numbers is 8, just like in here, 8, just like in here, 8. And 8 has 3 0 bits at the end. So that difference will help you out with modulo arithmetic too. That's exactly what happens those reminders, right? If I were to draw the reminder, say, modulo 25, once I get to the last reminder, 24, and I add 1, what's my next value? That will be 25, but 25 is not a valid reminder, modulo 25. So what's the actual reminder that happens there?
0.
0. So it's the same principle of this circle. Things start moving. Now for computer science, for binary representation, I don't want to be in this situation. This overflow means I'm getting a number that's too big for my ability to write it down. It's like if I use what people use usually for integers, like by default, if I say, give me an integer, how many bits are usually integers represented on? By default. If you don't, you can specify, but if you don't specify, we say C or Java, how many bits do you get?
I think it's 32.
32, right? So 32 bits means 1 byte, 4 bytes, right? 4 times 8, each 8 bits is a byte. So what's the maximum value that can be represented? Yes.
2 to the 32 minus 1.
Maximum integer would be 2 to the 32 minus 1. That's the same like in here. Here, how many bits do I have? 3. So maximum integer possible to represent is 2 to the 3 minus 1. That's a 7. In here, the maximum integer will be 2 to the 4 minus 1. That's 15. Same principle applies. If I am to add 1 to 15, I get 16. But 16 cannot be written on 4 bits, right? I need 5 bits for 16. So 16 will be 1, 0, 0, 0, 0. That's 16, right? And then this one here will be 1, 0, 0, 1, 0, which will be 80, so on and so forth. So the principle of going to this circle to the overflow and the difference remain a power of 2 stays the same no matter how many bits you have. So if you get an integer and you get to this value, anybody knows roughly how much this is?
2.1 billion. Oh, no, 4 billion.
2 million? Anybody else? Roughly. I don't mean with a calculator, that's cheating. 2 to the 32, we're talking 2 millions, 20 millions, 3 billions, 300 billions, 3 trillions? Like roughly, give me a ballpark.
I think it's like 2.1 billion.
2.1 billion?
I think that's 2 to the 31, and then 2 to the 32 is 4.2 billion.
Okay, so you guys should figure this out. I'm not gonna say after the lecture. How much is this? We talk about billions, millions, how much is it? Question? I think it's useful to know when you write the program and you say, I use integers on 32 bits. Well, are you gonna get into overflow problems? Because if you use, your Facebook and you have more than 3 billion things, maybe you're getting out of the range there. Maybe not. Like the weather systems can easily get more than 3 million things. The observations they have in those weather patterns are in the tens of billions sort of things. So you got to be careful. Do I have enough bits to write my numbers down? Right. So that's what I want to kind of tackle a little bit next. How do we think of this? How many things can we represent? Obviously from these circles, right? I can represent 2 to the 32 minus 1 things by exactly doing this. But I want to think of this maybe for the 4 bits ones in a slightly different way. So one way is to do the circle, and you see all the values that I can represent on 4 bits in this circle. I think everybody understands that. In binary, just do +1. I want to think in a different way of the same exact thing. How many bits do I have? Remember, I like those dashes that say how many spots are in here. 4 spots, right? 4 bits. So I would like to know how many things can I write on 4 bits? That's my question. So let me write it down. How many numbers or values can be represented on 4 bits. I'm going to go a little further with a preview of our next module 3 weeks from now when we do counting. And I'm going to say, you know, since my representation, every bit is 0 or 1, right? I'm not going to count necessarily values like numbers. Maybe somebody, instead of representing numbers 0, 1, 2, 3 up to 15, wants to represent colors or people. Here's 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. No, I can assign those values. If I don't want to assign them to numbers, I can assign them to classrooms or colors or you know, soccer games, right? I'm really asking how many possibilities are there? And how many ways can I put 0 and 1s on 4 bits? How many different strings of 4 bits do I get? Clearly, those are my possibilities here. And that's kind of like a brute force, right? I mean, it's going to try everything. If you look around, every single way to put 1s and 0 on those bits, it's somewhere in this circle. Can I do that directly without drawing all of them? Can I say, you have 4 bits. This is how many possibilities you have. Done. Like, I don't have to draw all of them just to count them. Somebody else. Yes.
I think the amount is 2 to the power of how many bits you're trying to.
Right, so his answer is, without brute forcing, check all of them, is 2 to the 4. Where do you think the 2 comes from? Why 2? Yes.
Each base can have either 2 values.
Right. Each bit has 2 values or possibilities, right? And where is the 4 coming? Why 4 and not 7? Yes.
4 total bits.
The 4 bits. Is this a general rule? Suppose I'm not in base 4, 2. Suppose I'm in base 7 and I have 5 digits. Here they are, 1, 2, 3, 4, 5. How many possibilities are here? 0, 1, 2, all the way up to 6, so on and so forth. How many possibilities are here? Total. 7 possibilities to the 5th. That is, there's 7 possibilities here, 7 here, 7 here, 7 here, and 5th of them, right? And effectively, we multiply it. 7 times 7 times 7, right? 5 times. Good. So this is something that we're going to study in more detail later, but I think everybody can relate to this principle, right? I want to reformulate this principle for you guys in a non-mathematical way. Virgil, your professor, has 2 pants, 3 shirts, 2 jackets, and 4 hats. How many ways can I dress up? If I have 2 pants, 3 shirts, 2 jackets, and 4 hats. How many total ways can I show up in class in different way? Like for the camera, I don't want to like look exactly the same in all the videos, right? I want to change a little bit. So how do you do that? Exactly the same way, right? Are we? The number of pants times the number of shirts times the number of jackets times the number of hats gives you all the ways Virgil can dress up. That is because every pant, I go with every shirt, with every jacket, and with every hat. Right? Well, that's not really. Sometimes I look really like it doesn't match at all. But let's assume every pant goes with every shirt, with every jacket, and with every hat. That way, every way I dress up, I pick a pant, shirt, jacket, hat, works out. How do I say that in here? Every pant goes with every shirt, with every pants, shirts, jackets, and hats. How do I say that? Every pant can be worn with any shirt, can be worn with any jacket, and with any hat. Can I say that for binary? Translate that sentence into binary representation. Every, what is this? Because it's not pants anymore, those are bits, right? So whether you put here 0 or 1, you can put here a 0 or 1. And you can put here a 0, 1, and 0, 1. In other words, there's no restrictions for if you put that pant, you cannot wear that jacket, that sort of thing. So if every possibility works with every possibility, so on and so forth, you get the product. So this is 2 times 2 times 2 times 2, because they are independent possibilities. Right? And all of them work together. All valid. This whole thing in here, it's called the product group, which you're going to use a lot when you do counting. If every pant goes with every shirt, goes with every jacket, I just multiply the numbers to get total number of possibilities. In interesting counting problems, you're going to have some restrictions. Even though you can do this product, the red pants don't go with the red shirt. So that's right there, an invalid combination that you cannot use. Or if you do license plates, you can't have all letters. You have to have some digits. So by removing possibilities, you obtain more interesting counting problems. But you should know this product group. Either use it with jackets and pants or with bits in binary. That's how many possibilities you get. If these 2 possibilities here, 2, 2, 2, and 2, you multiply them, you get 16 possibilities. And for checkup purposes, here they are. These are the 16 possibilities that you can get. Sounds good? I want to add one more thing to this whole discussion with the bits. I want to say, here are my bits, right? If I am to play a game, say I have a hidden value in my mind, and you have to guess it. If you're to guess it in binary, by asking questions, you can ask me questions, and the answer to those questions is binary, yes or no. What kind of questions would you ask? Pick any value in binary. For example, the game is guess value in binary. And let's say my value that you don't know is 0, 1, 1, 0, 1, 6 digits. So that's known that there are 6 digits, 6 bits. What are the obvious questions you can ask if you have 6 questions to find out this value? Yes?
Is the first bit 1?
First, you mean maybe most significant? Doesn't matter in this question. Is this one 1 or 0? That has a binary answer, yes? Yes or no. So in terms of logic with the tree, it's either that way or that way, right? And then what's the next question?
The same thing for the next significant.
So if you ask for every single bit, you know there's six bits. You ask for every single one. Is it 0 or 1, 0 or 1, 0 or 1? You ask 6 questions, you're going to get the value, right? Hands up, who's with me on that? That sounds easy. Now suppose you guys heard of binary search, right? In binary search, what is the question being asked? In regular binary search in base 10, I don't get to ask in binary search, is the first bit equal 1, right? What is the kind of question we're asking in binary search?
Like, is it greater than or equals, or greater than or less than this value?
Okay, so now I want to kind of move this whole guessing argument to transform it into binary search. In binary search, I can't ask is the first bit equal 1. That's not allowed. What's allowed is, like she said, is it greater or equal or less than some particular value. So now I pick a random value. I don't even know what it is here. Who is this? 2 to the
5.
5. This is 2 to the 3. This is 2 to the this is 2 to the 0. So the total sum is 32 plus 8, 40 plus 4 plus 1. Is that 45? So what's the first question that's being asked in binary? Let's go more specific. Greater or equal, that binary search algorithm is asking which value first? Somebody else. So it's true that that's the question, but what is the first value being asked?
Halfway.
Halfway through a range. I have to specify a range. So range is in here, right? If I say 6 bits, I'm going back to my table here. What is the range? The minimum number is 0, and the maximum number on 6 bits is? We did that last time, right? on 6 bits, you can get to 64. So you can get to 63. So now that I know the range, back to his answer, what is the first value binary search is going to check? Remember, 45 you don't know. I know that. You have to guess it. What is the first number that binary search check against? Is my value greater or smaller than? 32. So the first binary search question, number 1, is it value, how does it compare versus 32? Why 32? Is the middle of the range, right? 32 is the range divided by 2. How many people heard of binary search before this class today? Almost everybody, right? If you didn't hear about it, there's no shame in that. You can read it up. It only takes 15 minutes to get it done. So you have this range. You say middle. Is bigger or smaller? What's the answer going to come for 45? This bigger, right? So the answer is going to be bigger. And then binary search does what? If you say it's bigger than 32, it recomputes the range. What's my range now? Since I know it's bigger than 32, the range is not 0 to 63 anymore. It's what? 32 to 63, right? So now continuing the binary search, asking in the middle, what is binary search question number 2? Value versus who?
48.
My range is 32 to 63 now, and I want to ask in the middle of that range. About 48, right? Because this is range middle. And the answer is going to be? I'm looking at my value here, 45. What's the answer? If I compare 45 with 48. Smaller. So my range becomes what?
32, 48.
47, I think. You see how this goes? After every question, I'm halving the range, right? Yes.
So if it goes down to 47 instead of 48, then why do we say 32 instead of going to 33?
That's a matter of how you organize your code to make it work. The standard way is to include the power of 2, that's 0, and to go up to the power of 2 minus 1. But you can shift it. It won't affect the asymptotic behavior binary search if you include the plus 1. So that's just a matter of how you implement the code. Make sure you don't have overlapping cases. Again, I'm assuming some of you or most of you heard, were familiar with binary search and how it works. Chop the rest in half, always go left and right. What I want to do now is to look at this representation and figure out what binary search actually does. Is there a way to put this down? What does binary search actually does? What are all those questions? If you look at the binary representation, what is the question? Knowing the range 6 bits, because you have to know the range. How are you going to check the middle if you don't know the range? You have to know it's between 0 and 63. What is the first question in binary? Is this value bigger or smaller than 32? Can you ask this question in binary? Somebody else? Yes.
If you make the leftmost digit a 1, is it bigger or smaller than the value you're going for?
I think that might be true, but there's a much simpler answer to that question. Again, I want to ask the same question. Binary search question 1 is the value, how does this value compare to 32? It's bigger or smaller? What does that mean in binary?
Is the value bigger than 32? If it's yes, it's bigger. If it's no, it's
No, I know that, but what does it mean in binary if I look at the binary digits? How can I ask that question in binary? Yes?
If there's a 1 in the 2 to the 5th place, and you know it has to be greater than or equal to 32.
Exactly. It's effectively saying, is this first bit 1 or 0? Because numbers bigger than 32 must have this value 1. If it's bigger than 32, the first digit must be 1. And if it's smaller than 32, the first digit must be 1. So I'm going back to the binary. Remember when I asked first, how would you guess this number? In binary, what did you say? Well, you'd ask if this digit or bit is 0 or 1, right? And now we say binary search questions, that's exactly that. Asking if this number is 32, at least 32, or less than 32. It's a binary question. Is effectively asking, is this value 0 or 1? Because for any number that's bigger than 32, this number here will be 1. And for any number up to 32, the first bit is going to be 0. How many people follow me so far? So I want you to take a moment when you go home and look at the notes or the video, say, wait a minute, is this question absolutely equivalent? If I can ask in binary, is the first bit 1 or 0? Is it the same like asking in decimal? Is this number at least 32 or not? And what happens to binary search after that? Once it identifies this number, said, okay, that's a 1. What does the second question correspond to, do you think? I'm asking, how is this compared, including that 32 as an offset, with a range between, 48, between 32 and 63 now? Isn't that asking effectively if this next bit is 0 or 1? Because every single value bigger than, at least 48 will have this bit equal 1. And everything that's between 32 and 48 will have this bit 1, but this one 0. So those binary search questions are effectively asking, is this bit 1 or 0? Is this bit 1 or 0? Is this bit 1 or 0? So on and so forth. And because we did this theorem with a number of possibilities, that is, if you have 4 bits, you have 16 values. You guys have to finish this proof at home. Binary search is optimal in the number of questions it's asking. Which is to say, how many questions binary search is going to ask if I have 6 bits? 6 questions. You cannot possibly find the value all the time if you don't ask 6 questions. Here's why. You have 6 bits. Every question is binary. It can give you a yes or no. So if you ask less than 6 questions, say 5, how many total possibilities can you get out of yes or no with 5 questions? At most. 32 is this argument right here. If you have 5 things to ask for and every one of them is 0, 1, 0, 1, remember the questions have to be binary. At most you can get 32 different answers. That won't cover the range. If you can get 32 different answers but the range is 64 values, you're going to miss some of them. So you cannot do with binary questions, whether you implement binary search or a different algorithm, if the questions you get to ask are binary, if you ask n questions, you can possibly get only 2 to the n answers. So you gotta ask 6 questions here because there's 6 bits. So that proves that binary search is an optimal strategy to deterministically find. You can't do it with less than 6 questions. Okay. Any questions about that? I know this is going a little bit fast and a little bit too advanced. I don't want to care about binary search, the algorithm. We're going to study that later. We're going to study product rules and some rules for counting later. What I want you to get you thinking into binary in an abstract mode, not just playing with 0 and 1s and add them up together and get the result. I want you to actually think of, okay, how does this play out to numeration basis? So you have to think of it this way with those dashes like me and say, if you have 5 digits, and this digit is 0, 1, this is how number representation works. All right, we all said with that. We have to do 2 things today. They force me with the regular homework to do those 2 things because you have to be able to do the homework. There's a homework that starts today and ends next week. So those 2 things are, first one is how do we deal with negatives? That's all very good, right? Everybody understood this? But I don't have any negative numbers there, right? So how do I do that? Yes, you have a plan for dealing with
That's
this?
my comment. So for the max int, so in like Java, for instance, the range is negative like
Correct.
2.1 billion.
So this is positive.
Yeah. So
range.
Yeah,
So I think it's called unsigned in most languages. If you want to get this value max, you have to start from 0 to the max.
Yeah.
So the good point, most languages, when you want integers, they give you both positive and negatives. Let's first state the obvious thing. If you want, say I have 4 bits. Of course, in Java or C, you have 32 bits by default, but we can't draw. There'll be way too many possibilities to draw 32 bits, so we draw 4 bits here, 60 possibilities. One thing that should be obvious, if I want to include negatives, I have to kick something out. I mean, if I already identify those positive possibilities, there is no way, if I only have those representations, which are 16, to keep all these positives and add negatives to that, right? I need more bits if I want to represent negatives, or if I want to keep this 4 digits, 4 bits range, I have to kick some positives out to make space for the negatives, right? Everybody's okay with that? Hands up? We gotta do something. We can't represent all these positives and negatives because we already used all the possibilities of representation. Now, the other thing that I have to say, I would, if possible, not read the book for this negative representation. And it's up to you if you read it or not. If I were you, I would try not to read it, with all the respect to the authors. I think that's a way to get confused about negative numbers. Because I did. When I taught this class for the first time, I was like, 2 complement. I was a mathematician, right? Like, I was very good at math, right? I should be able to do it very fast. I go read the book. What? And it's like, I don't know how that works. So if you want to read the book, it's correct. There's nothing incorrect in the book. It's just a matter how well, you know, you have to have fluency. Those things have to happen fast in your mind, in a quiz, and when you use it in a computer, you have no time to think about it. So what is the easiest way to think about negative numbers? That's up to you. Every way is good. There are 3 or 4 different ways to think about it. I don't like the one in the book. So we're going to do that as a theorem. We're first going to do negative numbers as a theorem. What the book says is correct. You get to prove that one. Here's how I like to think about it. I want to say, what happens if I do -1?
Go backwards.
Right, you go into negative numbers, right? So if this is 0, and I go back in the circle, what should this be?
Negative.
Negative how much? -1. And if I go back again, -1, what should this be? Right? That's it. That's the story with negative numbers. That's my way of understanding negative numbers. If you start from 0 on this circle, you go one way, you get the positives on the right side. If you go the other way, you get negatives. Now, the advantage of the thing is I've done explaining it in like 45 seconds, right? The disadvantage is it's quite tedious to work with this mechanism. I've done it on quizzes, you know, and on exams, and it worked out. Sometimes I was tight with time, but I never get the answer wrong, as opposed to other people who use the book rules and done it much faster than me, but sometimes got it wrong. So that's my way of thinking of numbers. The question is, now I have this range, right? How much do I go? Clearly, I have to sacrifice some possibilities. If I say this is -1, it can't be 7, right? It's either, if it's a positive range, I go from 0 to 7. If it's negatives and positives, like programs do, like you declare an int in C or Java or Python, you get positive and negative range. You have to decide how much you want positive and how much you want negative. So you can go up to -4 here and say, okay, I don't have a 4 because it's -4. Remember, you have to choose one of them. Or you can stop at -3 and allow the positives to go to 4. What is the standard range? If you say, I want an integer on 3 bits, how much is negative and how much is positive? Anybody knows? Somebody else? Yes.
Is it that you take the highest positive bit, divide it by 2, and subtract 1?
I want an answer. How much do I go with the negatives?
To the -3?
No. I go to -4. So the negatives are -4, -3, -2, and -1. And the positives are 0 counts as a positive for this mechanism. You'll see why in a second. 1, 2, and 3 are the positives. How about if I have 4 bits and I apply the same mechanism? I can't do 15, 14, 13, those guys, because I have to sacrifice these representations to make space for the negatives. So who's this one now?
Negative 1. Negative 2.
So I cut the positives to make space for the negatives. And where, up to where do I go with the negatives?
Negative 8.
Up to half of the range, right? So remember how many possibilities I have here? Total 16. The number of possibilities didn't change. If you have 4 bits, you can only represent 16 items, whether they numbers or students or universities or colors or food plates, whatever you want to represent on 4 bits, you can't do more than 16. We said that in here, number of independent possibilities 16. So I still have 16, I just have to decide how many of them are negatives and how many remain positive. And the 2's complement representation, let's write that down. Maybe there, up there. Oh wait, we need this circle here. Two's complement says 0, say, we have to specify the number of bits. On this one, it's absolutely necessary to know the number of bits. If you get a problem, quiz or exam with 2's complement, it doesn't state clearly the number of bits. You have to ask that question. You cannot do 2's complement if you don't know how many bits are there. If you look at representations of, say, pick a number, -2, what is on 3 bits? What is it on 4 bits? Clearly different, right? So you have to know the number of bits on 2's complement. So let's say 2's complement 4 bits. Of course, this works the same, any number of bits. Where is 0, 0, 0, 0? That's in the middle, and that corresponds to 0. That's like in the positive range. Nothing funny so far. So the positive range remains kind of normal, you know? Nothing weird about the positive range. If I add 1, I get 0, 0, 0, 1, and this corresponds to 1. And if I add another 1, I get 0, 0, 1, 0, that corresponds to 2. And if I keep going that way, but I keep track of where is the last one, I don't want to go over the last one. What's the last one I can represent? Which is who? 0, 1, 1, 1, that is a 7. And we call that the positive range. How about if I go backwards on that circle? If I want to do -1, who's that? -2? And the last number I can represent is who? Look at the circle on there. Which one is the last negative I can represent? -8, which is who? This is the negatives. Can you tell me the simplest possible way to say if a number is positive, negative in 4 bits representation? Yes.
If the first bit is 1, it's negative. First bit is 0, it's positive.
Clearly, all the negatives start with 1, and all the positives start with 0. So let's write that down. Positive, most significant bit, that's on the left side, equal 1, 0. And this is most significant bit. Again, the left bit is 1. So if you just want to know, this is called a sign bit. The sign bit is the first bit because it's going to tell you it's a normal positive and this is a negative. Now, who would have guessed 1, 1, 1, 1 counts as -1? Like when I heard this for the first time was a long, long time ago, you know, because I was curious. And I'm like, who can possibly come up with such a schema? Right, I understand the circle, right? Fine. Because you got all the way to 1, 1, 1, and you kind of want to go back with -1, makes sense to, okay. But it looks really weird to say 1, 1, 1 is -1, right? And that's not the weirdest. Imagine if I pick something in the middle. Suppose I pick something like it's in here. If I would have asked you, guess who this is, 1, 0, 1, 1? Who would have guessed -5? In fact, if you want to make fun of somebody who didn't just study 2's complement, you tell me who -5 is in base 2. And they will never get it right. And there's no way to guess that particular number. So, does it make any sense? Why use this representation? Now, to be clear, representation is a matter of convention, right? Would it be wrong to say, wait a minute, this is -3, -4, -5, -6, -7, right? All of them. So what if I say 1, 1, 1, 1 is -3, 1, 1, 1, 0 is -7, this one is -5, and I just choose a different convention. Isn't this like a dictionary, like a map? If I just put them in the dictionary, right? I still have all the 16 values from -8 to 0 and then to +7. It just, I choose to not represent -1 with 1, 1, 1, 1, but rather -3. Would that create any problems for me whatsoever?
Well, it creates problems when you try and do it.
Like?
If you say -1 plus 1.
Right. So the reason this is a bad idea, and this is a very good idea, is because what happens when you try to add or subtract numbers? In fact, I lied a little bit. This is not how I get the representation. It's correct. It's one way to get it. It's just way too hard to solve problems. If you do on a quiz something like this with a circle, you're not going to finish in time, right, the quiz. So how do I get to -5 on 4 bits? If I don't have a circle, right? I have to get a different mechanism. Somebody who didn't speak already. Is there a way to get to -5?
11.
So he's saying it's like 11, and the 11 is in base 2 something, which is?
1, 0, 1, 1.
Is that right? Check it out. Is there -5 in there? But the problem with this mechanism is, how did you get 11?
I just imagine like you turn the clock forward as though it's positive, so just add
You use the circle.
Yeah.
And I just said, I think that's totally correct, but I'm not sure. If the number has 7 digits, or 8 or 12, can you still play with that circle in your mind to turn it around and get to 11? I'm just saying, it seems complicated, right, to turn that circle. So let's hear somebody else. Yes?
First digit is like still 2 to the 3rd, so it's not negative 2 to the 3rd.
The first digit, hold on, is what?
The most significant bit, it's normally 2 to the 3rd, but now we're going to make it -2 to the 3rd.
So first of all, why 2 to the 3rd and not 2 to the 5th? How did you pick the 3rd power?
Just because when you're writing bits in general, like the most significant bit is just 1 minus the amount of bits, like the exponent.
Right, but why 3rd and not 5 or 6? I think you mean because I say 4 bits.
Yes.
Right, so 4 bits. Again, what I do when I hear 4 bits, I draw 4 dashes. So I don't get confused on how many spots are there. There are 4 spots. And what he's saying, the first bit is the normal 2 to the 3rd.
But it's not negative.
It's positive?
No, like, so normally, like, if you just had 1, 0, 0, 0, that'd be like 8. But now we're gonna pretend that's negative 2. And then for every other.
So that's 8.
But for negative values, that's gonna be negative 8.
All right.
And then now every other value is just gonna add to that. So if you wrote like.
So you add, say, something to get to -5, is that it?
Yeah.
Right. So that's a plan. How much do I need to add to get to -5? 3, right? So who's 3 in binary? Is that 3? So if I add them, it's just normal addition, right? 1, 1. Do I get the right answer? I should get it because this has to work out. This requires knowing the -8 is the one you need. So what he did effectively, he said, you know what, I know -5 is a negative. So it's gotta be the minimum possible negative, that's a -8, plus a bunch of something positive, right? Because to move on that direction, you have to add something. How much do I need to add in my case? 3. So I know the positive representation of 3. And that's always going to be a positive because I started with the leftmost negative. How much do I need to add to get to my value? Requires doing this in base 10 though. A minus 8 plus 3, if you screw up this calculation, that's going to go bad too. I kind of have a different one. I think this is perfectly fine if you don't get lost in it. Yes?
You can take, basically you represent the magnitude of the negative number in binary.
What
So-
negative number? Minus 5?
Sure, minus 5. So you'd put 0, 1, 0, 1.
Oh, you mean positive 5?
Yeah, you take the magnitude
0,
of that.
1, 0, 1, yeah.
And then you just flip every single bit, so it becomes 1, 0, 1, 0. And since you only have 1, 0, you don't have a positive 0 and a negative 0 on the circle. You add 1, and then you get 1, 0, 1, 1.
You guys knew this magic rule of 3 steps? Write in positive, flip the bits, add 1. That's the one from the book that I never get right. Like I said, if you can remember this and do it on a fluency basis, like in your head when you need to, that's great. It's a perfectly correct mechanism. You know what happens to me? Sometimes I forgot which order those things go. So I'm like, do I have to add 1 and flip it, or flip it and add 1? I'm lost sometimes. I'm serious. I'm not kidding. Sometimes I'm kidding, but now I'm not. I don't remember that one. Yes.
Can you just add the number of possibilities to your number?
I think that may work. Let me tell you the one I use, and if you find it complicated, use one of the other ones. Just for reference, I think the circle is the most difficult one to use in practice. What I try to remember at least as possible. Because when you're a professor, there's so many things going on, you don't want to remember a lot of stuff. So I say, look, minus 5, I don't know what it is. Right? I know it's 4 bits. Why? Because I said 4 bits. But I know what plus 5 is, just like he said. What is it? 0, 1, like that, right? And I know if somebody were to add minus 5 to plus 5, supposed to get what? Right? So I'm start asking, okay, well, I need to get a 0 here, right? So what do I need to put in this spot to get the 0? Only 1. So now 1 plus 1 gets 0 and the carry bit, right? So now 1 the carry bit plus the 0 plus what do I need here to get a 0? I need to get a 1. You follow my calculation here? And then this will be also a carry bit, right? So now I have a carry bit. I have a 1 the carry plus 1 that I have, plus what I need to put here has to give me a 0.
Yeah.
What do I put there? 0. Do I have a carry bit?
Yes.
Yes or no?
Yes.
Yes.
Didn't I do 1 plus 1 plus 0? Is that a carry bit?
Yes.
Right, I have a carry bit. So carry bit plus 0 plus what will give me 0? 1. And now I have a carry bit. 1 plus 1 plus 0 give me 0, but is there a carry bit for the next column? Yes, there is. So minus 1 plus, I have nothing here, and I have nothing here. Why is that? Why is not important what I get here? Because it's 4 bits. That's an overflow. Whatever that value is not going to be in the memory. It's 4 bits, so it doesn't get counted. So see how my mechanism works? I think it's slower than some methods that people said here, but faster than the circle. I never failed with this one. All A grades in math. This method. What do you need to add to get the 0? Simple, easy to remember. I don't have to remember the minus 8, minus 16, minus 32. I only have to remember 0. Takes no effort at all. But the book insists on this rule, so you get ahead and use that. Just don't get lost in it. I would propose a theorem that says rule in the book is correct. That is, if you do this, positive, add 1, flip, and then add 1, right? Then you get a 0, then you get the right number, right? Try to prove that. Because the right number is defined by the circle, right? So you have to prove that you get the right representation of minus 5. Or, I think everybody can believe this one. If you get something that added to plus 5 gives you 0, that got to be correct, right? Because there's only one thing that added to plus 5 gives me 0. So I think that's the one I use the most. There is suppose I do want to use this extra column. Just I have a memory spot in my head that's not in the computer, but in my head I have a fifth digit. What will the digit be in here? The +5 will have what in here? If I am to write it, 0. So what would this be if I have a 1, 1, and this would be a? If you continue to do this, if you keep adding things, you're gonna get 1, 0, 0, 1, 0, 0, so on and so forth. You see all these guys are negatives. Like 1, 1, 1, 1, 1, which is always, no matter how, if you represent it on more bits, the positives do what? When you say instead of 4, have 5 bits or 6 bits or 7 bits. What are all these bits in the front? 0. But if you extend the range for negatives, what happens to the bits in the front? The same -5 was 1, 0, 1, 1. When I say, okay, represent on 5 bits, what happens to this bit? 1, 1, 1, 1. So that's how they extend the ranges from 4 bits to 5 bits to 6 bits, so on and so forth. And here there is a little bit of magic that explains why it's called 2's complement. The reason for 2's complement is that if you add those what does the flip actually does? Flipping the bits. Can you express that mathematically? How can I do an operation that effectively flips the bits? Yes. What is the operation? I have a value, and I want to get flip bits of the value. What do I have to do to flip the bits? I know what flipping means, 0, 1, 1 to 0, but you had an answer?
Yeah, subtract from 2 to the power of the amount of bits.
Right, so I have to subtract this value from what? 1, 1, 1, 1, 1, 1, right? That is what flipping the bits. If you take a bunch of 1s, how many you need? 4 or 5, depending on the representation. And you subtract a value like 1, what was it? 0, 1, 0, 1, right? Say I use 4 bits. 1, 1, 1, 1. Minus the value, right? You see how this does the flipping? If I started with 1, 1, 1, if I subtract a 1, what do I get for this bit? So 1 minus 1 gives me a 0. Is that a bit flip? And if I subtract a 1 from a 0 from a 1, you understand what I'm saying? Let me do it this way. 1, 1, 1, 1 minus 0, 1, 0, 1. Every subtraction is going to flip the bit. If this is a 1, that's going to be a 0. And if it's a 0, that's going to be a 1. So flipping the bits, it's effectively subtracting the value from 1, 1, 1, 1. And now back to what he said. Who's 1, 1, 1, 1? It's 2 to the k minus 1. Right? So why this works, this rule, is because flipping the bits means subtracting the value from 2 to the k minus 1. So let's rewrite this rule here as first flipping the bits 2 to the k minus 1 minus the value, and then the last step on the theorem was what? Plus 1. Plus 1 cancels with a minus 1, and you can see now why this is a correct representation. If this is a positive plus 5, that's what I started with. When I end up doing all this, I'm going to get power of 2 minus that. But power of 2 is effectively 0, 0, 0, 0 because the 1 in the front doesn't count. So this is saying take the positive, subtract it from this 1, 1, 1, 1, add the plus 1 to get rid of this minus 1 here, and then this corresponding thing plus the value will be 2 to the k, but 2 to the k is 0 because it's back to the circle. 2 to the k for 4 bits will be 16, which is 0. And for 3 bits will be 8, which is 0. Yes?
Can't you also just add 16?
Right, that's equivalent to the minus 8. I start with a minus 8 on the circle and move it. I think the circle is the easiest and cleanest way to not be wrong. It's just too tedious in practice. If you start drawing the circles for 5 or 6 bits, it's just going to be hard to rotate them. But I think it's the easiest way to not make mistakes. How much time we have left? Right. Let me do another example quickly so you guys can do the homework. And I think we did 105, somebody here? That one, correct? How about I have an example here. How about 83? Can somebody tell me who this is? In binary? Like, what's the fastest way to get this in binary? 2 to the 6 plus? How much I've got so far? 80. Now, who's 3? So, this one is 1 followed by 6 zeros, right? 2 to the 4 goes where? Here, right? 0. 2 to the 1 goes here. 1. Is that true? So I've got that for 83, and I'm going to read the 105 from there. So let's say 105 is, how much was it? 110, right? 100. Let me write a little bit more. 110, 100, and I got 83, which is?
There was a 1 at the end.
I missed a 1 somewhere?
Yeah,
At the end? And then 83 is 10, 1, 0, 0, 1, 1. You got to make sure you align the bits when you do operations from what side? If you have different number of bits, you align them to the right, right? In this case, I have the same. If I want to add these guys, what do I get?
0.
0.
1, 0, 1.
If I have enough bits, I can have this other 0, and that should correspond to what happens if I add those things?
188.
188? Well, somebody can check that to see if it's correct. What happens if I subtract it? 105, again, it's 11, 01, 001 minus 83, which is 101, 00, 11. Now, how do I do the subtraction? I want to do it like first brute force. Like, can I do 1 from 1 gets a 0, something like that? And then 1 from 0?
You have to
1, and keep a carry bit of minus 1. And then, what do I have here? 0 from 1 is?
1.
And then here I have something?
Minus 1.
So what is this? 0 from 0 is?
0.
And then 1 from 0 is?
1. Minus 1. So 0.
And then 0, 0. How do I know if this is correct? Like, don't ever leave a result like that. Because that's a great way to lose points.
Oh.
I can do it in base 10. I'm supposed to get what? 22. Is this 22? This is 16?
4. 2.
Works? Now, what's the other way of doing it? Is to do 105, 11, 01, 001, and then minus 83, right? Because I want to add them now. Can we flip the bits and add 1 in our heads in here?
Yes.
That's a procedure, right, from the book, the one that I said I'm not so sure it works if you don't remember it exact. But let's see, what would that be?
0,
0, 1,
1, because this has to be at a plus 1, right, after flipping the bits. So the flipping the bits are 0, 1, 0, 1, 1, 0, 0, plus the 1, right? We have to verify this. So now let's do the addition. 1 plus 1? 0, 1, 1, 1 plus 1, 0, carry bit 1. There's something here, but we're not going to write that one down, right? So is it the same? Same. Okay. So I could do the subtraction either way. It's going to work out. Good. So that being said, I really don't want to do this today, but you have a homework and the recitation and all that, so I have to do a little bit of it. And I'm just going to give you enough so you can't blame me for not being able to do the homework problems and say, see, I did like 45 seconds of it in class. You can't say, hey, I didn't know that. But the truth is, we're going to do Friday a lot of it. So for the homework, no problem. And for the recitation, you know, we are on our time. We don't have to, be at fast pace. So what I want to say is, how do you think of circuits and binary with wires and with logic? You get true equals 0, that's true, and f true equal 1, and f equals 0, that's false. So what I mean to say is, you get those Boolean variables, A and B, and because they're Boolean, they can either be 0 or 1. And I'm sure you already know. You can write true or false on these things if you want. I think you've seen this before. T is 1, F is 0. There's only two values. And there's an operation that's called A or B. This is called OR and has a gate in circuits, a representation that is like this. Kind of. And the meaning is the common sense logic. False or false gives me false. False or true? True. True or false? True. True. True or true? True. And the easiest way to think about this, if you've never seen it, which is fine, is to think common sense of OR. What does OR means? You know, I either get a good grade in CS 1800 or a good grade in CS 2500, the funders. What does that mean? You know, am I going to be happy at the end if one of those grades are true or one of them? Maybe you're happy if both of them are true. In each case, you need this, which is called AND, and it's drawn like a round thingy here. So this to be happy with both grades, what's the only case that makes me happy? One. Everything else makes me unhappy. And I can also add here negation, not A, which the gate corresponds to something like this. It's called not. That only works for one variable, so not of 0 is 1, not of 0, 1, 0, 0. And I would like something extra to add for you guys that the other people don't see here. I would like to add the implication A implies B. That is, from A, I can get to B, inference, so to speak. So what do I get? When is the implication true? Or when it's false? We kind of mentioned this last time. Logically, if I want to say from here you can get that, which one of these 4 cases corresponds to true and which one is false?
When A is true and B is false.
A is true, B is false. This case is which one?
When
is that false or true?
That makes that false.
That makes it false equal true. So that's saying 1 implies 0. That's the only case that is false. Everything else, the implication is true. So this case here corresponds to this box. So the implication 0 implies 0 or false implies false, that works out. False implies true, that works out. Maybe that's counterintuitive, but it does. 1 implies 1, true implies true, that works out. The only time the implication is false, it's true implies false. That's the only time when this operand gives you false. And then when you draw circuits, you draw stuff like this. You say, hey, here's A, and you know, here's not A, because you get a connection from here. And that's not A now. And if you want, here's B, you know, and if you want to do A times B, you put a gate here, you know, and you can say that's A times and B, because I have A, B, and that comes out of this gate. This is the AND gate. And if I A or B, I can draw another connection from here and one from here and say, well, this I want to be a different thing, which is A or B, and so on and so forth. So this is the not A that I could use here together with, say, B. If I do an AND, I get not A and B. So I can draw these things and obtain values of the series. The way this works, you put either 1 or 0. If A is 1, not A will be 0, of course, and if A is 0, not A will be 1. There's no magic at all in this thing. I think this, intellectually speaking, is like a 5th grade exercise. All you have to do is to go through the notes and do enough examples, so don't get lost. It's like drawing wires is not a thing. Now, I want to show you the website for a second. If we have, at one time we have until. So that's enough time to show you the website. Okay, quiet for 1 second. What's happening on the website? There is the book notes. You click on them, you get my lecture notes. They are written by me. They're written by Professor Aslam, amazing professor. So those are the regular stuff. If you click on these other things, you get the honors discussions. Like here, we talked about binary search optimality. It's this one right here. You can also click on the recitation. By Tuesday, this should be up. We'll bring those papers with us, but if you want to download it today and start working on exercises, be my guest. If you don't want it, you can wait until tomorrow and you get this paper tomorrow, but you have to wait in class. Some people would want to go and start thinking about these star problems because they're definitely not solvable in an hour. Maybe not at all solvable, who knows. So this is clearly optional stuff. If you're interested in the star problems, you should look at them. There's a homework 1 right here. That's homework 1. And I put here a bitwise operation code. It's in C++. That's also optional. You can play with it. You can download this code and run this code. If you do, you're going to get stuff like this. I will run it next time in class. But if you do, it has to compile because it's C++. It has to do with how numbers get represented into bits. So you may have to change the code in there. Has a bunch of checks. Let me just show you this a little bit. So if you remove one of these returns and you rerun it, you get more stuff. But you do not. You have to remove this one. But the point in here, if you put enough values somewhere here, you observe the overflow, for example, as the first exercise. If you know how much those numbers should be when you multiply them, you're going to notice this is not the right result because it overflowed for the bits I've been using. And if you play with this code, you get to see for a bunch of real and integers the actual representation in bits. So the code plays with that. It's called bitwise operations, and they're quite useful in practice when you use direct memory access like pointers in C++. So if you want to play with this code, please be my guest. It's not necessarily part of the CS1800, but it gives you a direct access to the bits of anything, not just numbers. Anything you represent in memory, you call this code, it's going to spit out the bits of that thing. So floating numbers will have 64 bits, and integers will have 32, and so on. All right. I'll see you tomorrow and Thursday at Rider 159 or Some people are
I'll look into that next time.
Oh, I'm class too.
Yeah.
No, I have. I think
I mean, I'm not sure if you